So let's get quickly introduced by a term called page attention, which is now extensively being used for memory optimizations as our LLMs are getting bigger and bigger. So when you load an LLM or for an inference, basically two things that gets loaded into memory are its parameters. For example, you can have an 18 billion model, you can have an 8 billion model. So these parameters get stored into memory. The second thing that gets stored into memory or your memory gets reserved for is the KV cache. Now, KV cache is a method that allows for faster inference. Basically, we'll deal with it someday later. But yeah, just understood there is a cache that needs to be stored. Now, what happens is basically paged attention do is it optimizes how your KV cache is stored. For example, in OS, let's relate it to the concept of operating system. In OS, when your process could be very large, the program which you're writing. So what happens is basically your OS or your OS basically breaks these processes into frames. Now these frames can be scattered across different memory locations in your RAM. Now, when a CPU generates address, it generates a contiguous blocks of address that okay, I need from here to here. Now, to map these addresses to the physical frame, for example, where is page one, where is page two, we need a page table. And this page table is maintained by the OS. So your external fragmentation gone, your internal fragmentation might be there, but yeah, your reserved fragmentation entirely gone. So these three fragmentations are what that is getting optimized in while loading and doing an inference from an LLM model as well over here. So what pays attention to? Very similar thing. So your entire KV cache gets broken down into blocks, now smaller blocks. And these blocks can be scattered around like different part of the memory of GPU. And you have just like virtual address translator, you have a page table stored over here, which basically maps, okay, where is this particular attention block is stored. And now what happens is, for example, you are predicting the next token. Basically, LLM will say, give me attention of previous 10 tokens. Your page table will look it up, will look that, okay, where are all these attention blocks stored? It will fetch them from there, and then it will provide to your LLM. The next token attention gets generated, and then you predict basically what your next token is. Now, this particular next token will be stored in the current block itself if there is some memory, or it will be getting stored into a new allocated block. For example, let's say your max sequence length is 2048. So rather than storing entire 2048 tokens in a single contiguous strip, this will be broken down into, let's say, a block of 16 tokens, and this all these blocks are scattered around the GPU. So this basically completely eliminates external and reserved fragmentation. There might be a certain kind of internal fragmentation because at a time we might not use the entire 16 token limit. But yeah, that's pretty much negligible. So this is an entire relation of page attention with virtual memory and then operating system. I hope you get an idea of how page attention works and then how it is used to optimize memory table. We'll try to cover up KV cache in some other video. Yeah, but then see you soon.